Today we are learning about the second fundamental theorem of calculus, and that rule, which is on your note cards, is shown here. The derivative of the integral from a to x, where a is any constant, of f of t dt equals f of x. And this basically tells us that the derivative and the integral are inverse operations of each other. Now, this one is really easy to show you why it works. Let's say that I've got d dx of this integral using the first fundamental theorem of calculus could be shown to be capital F, the antiderivative of f of t, with the upper limit x plugged in minus capital F of the lower limit a plugged in, which a is any constant number. And then when I take the derivative of a difference, I can take the derivative of each piece individually and subtract those. And the derivative of capital F of x means we're going to undo the integral that we did, so that's going to leave us with little f of x. And then the derivative of f of a is going to be a constant number since we've plugged a into it. And the derivative of a constant is 0, so that just leaves us with f of x. Now, as a shortcut on these problems, because you certainly don't need to do all this work, this rule allows us to just take this x on the top and sub it in for the independent variable in the function listed here to get the answer that we're looking for. So we'll do a few examples of this pretty easy lesson. So, first one, the derivative of the integral from 1 to x of t cubed dt, bracket, equals, so all I do is take this x, put it in place of the t, and that gives me my answer, x cubed. The end. That's all you have to do. It's just that simple. Okay, the next one, the derivative of the integral from 0 to x of the square root of t squared plus 1 dt is equal to, take that x, put it in place of the t, that gives me the square root of x squared plus 1. And I'm done. Now, the next example is going to involve the chain rule. And it looks like this, d dx of the integral from pi over 2 to x cubed cosine t dt. Now, the reason that this one involves the chain rule is because I don't just have x up here. I have a function of x. So you'll have to use this anytime that upper limit of integration is not just x. And all you have to do to use the chain rule version, though, is it starts out just the same. It's going to equal the cosine of x cubed, where you're going to take that and put it in place of that independent variable. But then you must multiply it by the derivative of that upper limit. So the derivative of x cubed is 3x squared. And generally we would write that in front of the cosine, so then no parentheses are required, and that would be your answer. So there is an extra step when there's a function at the top instead of just an x. Now, this last example is the most challenging, and you're not going to see this come up very often at all, but I would not be happy if I hadn't shown you how it works. The derivative of the integral from x to 2x of the sine of t squared dt. So the problem here is this lower limit of integration is not a constant, and that requires some kind of clever thinking on our part in order to make this work out. So this rule, the second fundamental theorem of calculus, essentially only works if that lower limit is a constant. So we're going to force the constant into the problem. So I'm going to change this using the additive integral property to the integral from x, and I'm going to split it up and put a constant on the top to 0. That 0 could have been any constant number. There's nothing special about me choosing 0. Of this function, sine of t squared dt plus, now if you'll remember, the next one's going to start at 0, so these are going to match each other, and go to 2x of the sine t squared dt. If you can't remember that property, you may want to review that from the other day. And now, remember the constant is supposed to be on the bottom, the lower limit of integration. So I'm going to take this first one and switch it by putting a negative in front of it. And now I can distribute the d dx. Essentially, I'm taking the derivative of a sum, so the derivative applies to each piece of that sum. And now it looks just like the second fundamental theorem of calculus. So the first piece, I'm going to send the x down here in place of the t. I do have this negative here in front, so that will still be there. Negative sine x squared plus, now this one I'm going to send the 2x down here in place of the t, but that is a function, not just an x, so I'm going to have to employ the chain rule there. So I'm going to say that this is the sine of 2x squared times the derivative of 2x, which is 2. And then I just need to simplify this. Negative sine x squared plus 2 times the sine of 4x squared, which is the answer. Again, you are not going to see very many problems that have this going on. It's kind of rare, but now at least you're prepared to handle it if you do see it. Alright, so that's pretty much it for the second fundamental theorem of calculus. The other piece to today's lesson is using the graphing calculator. Ooh, my handwriting is just atrocious. To calculate integrals. Okay, so you're going to need your graphing calculator. If you don't have it handy, you better pause the video, go get it, and be ready to use it. I'm going to show you, using this example 5, how to calculate an integral in your calculator. And you're going to want to get pretty good at this before next class period, because we're going to use the calculator to solve some integrals there. So there's actually 2 different ways that you can do this. The first way is graphically. So I'm going to show you both ways. You're going to go to y equals, and you're going to type in this function that is the integrand of your integral. So y equals 2x cubed. And then you're going to hit the graph button. Then you're going to hit second and hit the trace button for the calculate menu. And then you're going to choose option 7, which has integral f of x dx beside it. The calculator is going to cue you. It asks lower limit question mark, Now you're going to type in the number that you have as your lower limit. So it's going to just be type the number 0. When you do that, it's going to appear x equals 0 on the bottom of your screen, and hit enter. And then it's going to say upper limit, and so you're going to type this number 2 for your upper limit and hit enter. And then it's going to give you the answer at the bottom of your screen. It's going to say the integral of f of x dx equals 8. And that's the answer for this integral. One thing that you should be aware of when you are using this method in your calculator is you must have both the lower and upper limits of integration displayed in the viewing window. So, you know, your standard viewing window is from -10 to 10 for your x-axis. So if you had to go from like 0 to 50, your calculator will only allow you to do that if your viewing window extends all the way to 50. So you do have to have the x-axis displayed for all values in this interval between the lower and upper limits of integration. Okay, let me do this same problem, another method. We're still finding the integral from 0 to 2 of 2x cubed dx. This is how you'll do it. Go to your home screen, so just hit second and quit. This is the same place you would start your calculator when you first turn it on. By the way, you must have the new operating system in order to use this method. So, if you have an older version of this calculator, it can be updated if it has a little port on the top that you can plug a link to another calculator in it. Some of those older black colored TI-83s you cannot update, so this would not be the method you'd want to choose. You'd want to do the graphical method, but this is on the home screen, and all of the classroom calculators have this, so if you need to use one of those in class, of course you're welcome to. You're going to hit the green alpha button, and after you hit the green alpha button, you're going to hit the window button. That's going to pull up a menu, and you are going to choose number 4, which has FNINT parentheses. That stands for function integral. So you choose number 4, and then it's going to come up with the little integral with a box at the bottom, a box at the top, parentheses, a box inside of that, and then D and another box. And you're going to just make it look like yours. You're going to type cursor over to the lower limit, type a 0, hit enter, arrow up to the upper limit, type 2, hit enter. Oops, no, don't hit enter. If you hit enter, it gives you an error message. Then you just use your cursor button, arrow over to inside the parentheses and type 2x cubed. And then last, arrow over to the D. After the D, you're going to put x for your, that's telling the calculator what variable you're integrating with respect to. And after you have that all filled in, you just hit enter, and it's going to give you the answer of 8 again. So there you go. Now, this is your last example. You can try this one in your calculator on your own using either method, whichever one, or you could do it both ways just to make sure you've got it. If you're doing this on your own, pause the video and then you can check your answer. So, the answer that you should have gotten is 10 2/3. Now, you might have seen this appear on your calculator as 10 point, and then a whole bunch of 6s and a 7. It's your job to know that that decimal does equate to 2/3, your calculator. Or you could hit math, frac, I guess. Math, enter, enter, if you wanted it to convert it. but I think that would make it an improper function, which would be 32/3. At any rate, 10 2/3 is the answer. So, short lesson today. Good luck with your second fundamental theorem of calculus assignment. Your assignment is a worksheet. It's actually a mixture of the problems that we've talked about today and the problems that we worked with last time. In fact, I think more of the second fundamental stuff occurs later in the worksheet. Some of the problems are challenging. They are just like real AP problems. And this is a very frequently tested topic on the AP exam. It's kind of one of their favorites. So be sure that you understand what you're doing, and good luck with it. Bye.